Hi everybody, welcome back. In this video, we're going to introduce a new kind of statistical analysis that we haven't covered at all before. First, I'll walk you through kind of why we need it, what circumstances it's appropriate for, and I'll also introduce a new example to you. And we won't do any calculations in this particular video. We'll work on that in the next one. So this will be the basic idea. So in a lot of statistical circumstances or research circumstances, we'll have variables or a variable that are not continuous. In fact, they're only categorical, and they're inherently categorical. Now, it may be this way for several reasons. Maybe that's the way you defined that variable for your particular research study, or maybe it's just that's the data that are available. Like, for example, maybe you're collecting data from a hospital or something, and they have data to give you, and you can't change anything about that data. You can't make categorical data once you have it continuous. If you didn't gather it that way, there's really nothing you can do. You can do the opposite, but that's beyond what we're doing here. So for example, you might have some kind of scenarios like a cancer diagnosis. Maybe you they want to do some research on sort of the outcomes of a lot of their cancer diagnoses. And so cancer diagnosis is inherently a yes or no. Okay, there's nothing continuous about it necessarily. We did the analysis and you either were found with cancer or you were found to not have cancer. Okay, so that kind of thing. Also, pregnancy would be an interesting one, right? There's no kind of in between. This is an inherently dichotomous variable or binary variable where it's either a yes or a no. It can be only two values, right? It's a yes or no, right? So maybe we would want to do some kind of analysis about that kind of thing. Maybe after a fertility treatment, we would want to decide yes or no, are you pregnant or not? In other scenarios as well, in like a legal context, there might be some kind of outcome of the trial. You were found guilty, you were found not guilty. It was a hung jury, it was a mistrial, for example. This is inherently at least categorical data. You could maybe argue that there's some ordinal properties there, but in any case, this would be perfectly appropriate as a categorical sort of variable. All right. Other things, of course, religion we've talked about multiple times through here. Religion would be an inherently categorical variable, again, and of course others, whether you finished high school or not. So in other words, the point is there are lots of categorical variables out there, and we may be very interested in using them in our analyses. And sometimes we're not able to design a study in such a way that it will provide continuous data. I will argue, however, continuous data, if they are available and if you're able to gather information using continuous information at continuous scale, it's probably better to do that. It'll give you a little more nuance and open up some new options for your categorical variables. However, sometimes we can't do that. Now let's talk about why that's a problem. Now, of course, when we have a continuous variable, we can calculate a mean and a standard deviation. But if we have categorical variables, that means that we have no way of calculating a mean or therefore a standard deviation, because of course the standard deviation requires a mean to define itself in the first place. So now if we have that limitation where we can't find some kind of central tendency, and by the way, we can't find central tendency because there is no center of the data, there's no central value if there's no order to those values that the variable can be. For example, religion. If you can't find a center value, then you can't tell me what the central point of that data set is. And if we can't do that, then we are limited in some of the analyses we can do. For example, if you do not have a variable that can vary on a continuous measure, it doesn't make sense to do a traditional correlation as we've talked about, because we can't, it takes some additional information to figure out what a variable is doing while another one is doing whatever it's doing. Okay, so our traditional correlation doesn't exactly work, even though we're not using means for that. However, we can't do mean comparisons either, because mean comparisons require means. And so if we have categorical data, no way to do any kind of mean comparison, such as a t-test or an ANOVA. So therefore, we need a new kind of statistical test that doesn't care about means or medians and doesn't need a standard deviation or any of that kind of thing. So these are, of course, limited tests, but they can still shed quite a bit of light on our variables and patterns within our variables. So these are called nonparametric tests. In other words, they don't have parameters. In other words, they don't have means or standard deviations. Okay, so we're not estimating the population parameter, at least of a mean or a standard deviation. We're just looking at patterns within these data and how they fall into their respective categories. The most common one is called a chi-squared analysis, and there are different kinds of chi-squared analyses, but we're just going to cover some of these simpler ones. And again, today I'm just going to introduce the basic idea here. Now, as I said, there are lots of different kinds of chi-squared analyses that you can have. There are also variations on the chi-squared analysis that are beyond the scope of what we're doing here. The simplest kind of chi-square, however, it looks at only a single variable, and it wants to know how the levels of that variable are turning out. What are the patterns going on in the level of that variable? I'll get more into that certainly here. We're going to practice one of those in the next video, and I'm going to introduce the basic concept here in this video. And then there's another kind that assesses the patterns between two or more variables. I'm going to demonstrate to you a two-variable chi-squared. However, I'm not going to go beyond two variables. That gets very complex. I took an entire course on that in graduate school, but it's beyond what we're doing for these relatively simple videos. Okay, and basically all the chi-squared does is it looks at the pattern that is present in the data we have, the actual data where we have some observations, and it compares the pattern in that data to a pattern that we would theoretically have expected to find if our theory is true, for example. So maybe we have a theory about the way the world works, and we can test out that theory. We can say, if my idea of how the world works is true, I should see the patterns appear this way in the data that I'm seeing. And if it's not that way, then I'll see the data appear a different way. And the chi-squared tells us whether we have sufficient reason to believe that it is the way that we theorized or different from that. And again, this will all make more sense with an example here. So let's try that. Okay, so I'm going to start off by introducing the absolute simplest kind of chi-square design you could ever do, where there's one variable and only two levels of that variable. So imagine this scenario. There's somebody named Terry, and Terry has two very close friends, Gina and Rita. And Terry gets in her head, maybe she wonders which is the better friend, and maybe the way she defines that is who is the first one to reach out to her every day, who's the first one to contact her every day. Now, we could talk to Terry about how silly that is and how there are lots of ways to be a good friend and all that. That doesn't matter, though. Just accept this for this particular scenario. So Terry wonders, and so she decides that she's going to keep track of who is the friend to contact her first each day, and then she does this for several days. Okay. So once again, just to clarify, we have one variable. The only thing that can vary here is the one thing that Terry is measuring, and she is measuring which friend contacts her first in the day, and it can be only two options, therefore it has two variables. In this case, it's either Gina or Rita. Now, if she has other friends who contact her first, she just doesn't count that because she doesn't consider them close or whatever, right? So just accept this for what it is, that she's going to just measure out of these two friends who's the first one to contact me. So every single time that she observes the variable, every day, it's either going to be Gina or Rita. It can't be any kind of third option. Therefore, again, inherently categorical. There is no ordinal property to this kind of variable, okay? So again, she's not keeping track, for example, of how frequently she's contacted. That'd be different. In that way, we probably could calculate a mean comparison. In this case, it's gonna be one value or the other every day. It's gonna be Gina or Rita, and it's not about frequencies. It's just about who's the first one, and then these counts as they occur. Okay. Now, she's interested then not only in who is more often the one to contact her first each day, because we could see that anyway. We could just look at the data and say, oh, well, it happened that Gina contacted you first more often than Rita did. That removes the entire point, however. The point of a chi-squared analysis is it meaningfully more, or do they actually have the same underlying likelihood of contacting you? You just, in this case, probably happen to see one of them contacted you more often. That doesn't necessarily mean that she's more likely to contact you. That's what we're getting at. And I'll continue to cover that, of course, as we go through this example. Let's start off with our two possibilities for the outcome. So, of course, what I'm talking about here is our null and alternative hypotheses, okay? Our null hypothesis, in this case, has nothing to do with means. It has nothing to do with correlation. It has nothing to do with anything like that because we can't calculate means. So what we're looking at here is probabilities. In other words, these are my symbols here. So my null hypothesis suggests that the probability of Gina being the first to contact Terry is the same as the underlying probability of Rita to be the first one to contact Terry. Now, that would suggest that there's no difference between them, right? They both are inherently the same sort of quality of friend, if that's the way you're interpreting it, and I don't see any difference. Now, here's the thing. It is possible that they have equal probabilities of contacting Terry, except it just happens that they contacted her at different rates this particular time, right? Or one of them just happened to beat the other to the punch more often than that one, right? So that's possible. Now, if we see enough of that pattern, enough of the difference from this, we can then accept this as true. And this, of course, is just the opposite. It says our alternative hypothesis is that the probability of Gina being the first one to reach out to Terry isn't the same as the probability of Rita being the first one to reach out to Terry. So then here's that same thing in words, as I just said. And again, the alternative there, just like I said, okay? So what we're interested in, again, is not necessarily how frequently they occur. We're going to use that to sort of assess whether these hypotheses are true. What we're really interested in is, are the frequencies different from each other enough that we can go ahead and assume that they have different underlying probabilities of being the first one to contact Terry? Okay. Yes, again, not interested in means, not interested in covariance, nothing like that. We're interested in the probabilities. And so it's a pretty common mistake for a lot of students to state the null and alternative hypotheses using means, which of course is not correct here. We're talking about probabilities. Also, you're going to have to keep an eye on these null and alternative hypotheses depending on the chi-squared design that we're using. Because if I had 3 levels of the variable, now I would need 3 options here, 3 probability options, okay? If I had 4 levels of the variable, it would need to be 4, and so on, okay? I'll go through several examples in these following videos, so just make sure that you keep track of that. And of course, you can see all of the other examples in my textbook. Okay, so her data that she gathers would have to look something like this, and I've just made up these data because Terry and Gina and Rita are not real people, okay? So you've got a table here, and every time she observes the value, in other words, every day, it would fall into either one of these boxes. And now inherently what Terry is interested in is this pattern that I see here different enough from what I would expect if the null hypothesis is true, that I can now say which one is the better friend, or which one is the one who's more likely to contact me first in the day, okay? So we'll talk about that in much more depth in future videos, but I'm going to leave it right there for now. We'll introduce the equation and then actually solve the equation and interpret it probably in the next video or a couple of videos. So I will see you then.